Well, first I want to thank Katharina and the other organizers for putting together this meeting, and also agreeing that I switched topics. I guess I was going to talk about Majorana work, which there is some new things I could tell you, but as you heard from Dima today, there is quite a bit of excitement about this topic of Moiré physics and Moiré superlattices. So I want to share with you some experiments we've been doing the last couple of years since this field has gotten started using STM. Okay, so let me see, my pointer doesn't quite work. Okay, so Dima gave a beautiful introduction to the field and also and all the transport phenomenology of this field. I'm going to be very brief with the introduction here. And I think the point I want to mainly make is that what's exciting about this system is that it sort of lies between two things that we are familiar with. As the picture that I have suggests, there is, of course, the correlated insulator phases that have been discovered with transport, giving us sort of this picture of Hubbard type phenomenology that we are familiar with from other correlated systems. And as I will show you, experiments really give us quite a bit of information to hang our hat on in order to connect what we see to this type of physics. But what is also exciting about the flat band physics in this system, just like we have in other systems in the past, the quantum Hall and fractional quantum Hall phases, is you have the physics of having topological flat bands. So this material system actually sort of sits in between the two physical systems that we are familiar with over the last 20, 30 years. So it's really opening up new ways just for theorists as well as us experimentalists to look at ways in which topology and correlations can work together. And so in this regard, we were very excited to jump into this field and to try to see what we can learn using spectroscopic measurements. So let me just orient you. These are things that Dimitri already pointed out. By twisting the angle to the magic angle in bilayers of graphene, you get separated out two very flat bands. This was predicted theoretically by Alan MacDonald and others. And immediately, of course, when we have flat bands, you can think about also in real space what you have. And in real space, just from this single particle physics picture, you get this the local density of states where electrons are living and having this enhanced density of state and these Moiré superlattice sites. So from a perspective of thinking about what we are doing in the experiment is we are basically loading electrons with a nearby gate into this Moiré pattern and being able to completely deplete and completely fill these two bands, which have two spin and two valid degrees of freedom, is something that's very difficult to do in condensed matter physics. You cannot change charge density in systems such that you completely fill and empty the band, and that's what gives this system its special property. The other special property it has is it inherits the topological, if you wish, the Barry phase that it comes from graphene Dirac cones. And if you zoom in on those flat bands, they actually have Dirac points. And this actually gives rise to the topological phases that you heard from Dimitri about when we start to cause perturbation on these Dirac points, either via single particle physics, or as I will show you through interactions, which is very novel. Okay, so what, of course, you heard in details about of the discovery of correlated insulator and superconductivity and the impressionistic connection between the phase diagram of the system and that of strongly correlated system like high TC or heavy fermion superconductors. So this is all very nice, and superconductivity seems to come out of an insulating phase, but what is nice about this system is that the ability to control a lot of parameters in a chemically clean settings allows us to actually quantitatively measure correlations rather than just make a sort of impressionistic comparison to a phase diagram. And this is actually the first part of my talk, which I'd like to show you. So as you know, my group does scanning tunneling microscopy, and over the years we do imaging, of course, local spectroscopy, where you measure the local density of states with a high energy resolution, and you can do spectroscopic mapping to map up how the density of state look in real space. But what excited us about 2D materials in general, and in particular this system with strong correlations, is that now we can add to the technique of doing spectroscopic measurement the ability to in situ tune the carrier concentration. So this is a very exciting knob just by itself from the perspective of being able to do new experiments using the STM. You can being able to locally control the carrier concentration and be able to actually go between, as I'll show you, interacting and non-interacting limit in the same clean material system. So for example, in the cuprates, we had to make samples with different doping and spend many, many months to study these using the same instrument. Here, we can just make one device, and with that device, we can actually span the whole range, and this is a very different type of control experiment. So it's taken us a lot of time to make very clean magic angle devices. I spare you the details. What you see when you make these devices, as Dimitri pointed out, you see that the stacking of the two different graphene layers on top of one another give you a roughly the AA sites, where the A atoms in the A graphene sublattice sits on top of the A atom on the other graphene sublattice, or you have AB stacking, where the A atom sits on the B sites and the bridge sites in between. From these images, you can immediately tell what the twist angle is, because the periodicity of the Moiré wavelength depends very sensitively at low angles on the twist angle. So unlike our transport colleagues, we can actually directly measure what the twist angle is from the experiment, and we can also assess whether these samples, which are often created on top of a boron nitride substrate, whether they're aligned or misaligned with the boron nitride underneath, which has its own Moiré lattice, which you can sort of see in these images, in this image right here. Okay, so now let's talk about the spectroscopic measurement. So we put these samples, they're on nearby a gate, and we can basically tune the gate in order to basically deplete and add electrons to the system. So let me first show you two spectra where the gate is such that we can fully deplete or fully occupy the flat bands in the system. So the flat bands gives rise to a large density of states, which gives you this peak in the DIDB measurement as a function of tip sample bias. So these two sharp peaks are two flat bands which have two spin and two Valley degrees of freedom within them, and you can see them below the chemical potential here, fully sharp, and you can see them above the chemical potential here, also fully sharp, and you can sometimes see the remote band also in these experiments. So the sharpness of these peaks basically tells you about the flatness of the band, which is about 12 or 13 millivolts in this system. Okay, so these are the Van Hoff singularity. In fact, if you take the STM images, you can even take into account the strain that you see in the STM image and input it into a theoretical calculation to actually understand the detailed shape of these spectra. So the single particle physics of this problem can be beautifully understood with the local STM measurement and using sort of the single particle machinery. Now, what happens next as you go into the partial occupation of the flat band, where the insulating and the superconducting phase arises, is very interesting in the spectroscopy. So what you see here are the two sharp peaks that I showed you, and what we're doing here is changing the gate voltage. And you see that this peak is moving towards a chemical potential, and it's basically remains sharp for some of the time. But as it approaches the chemical potential, you can start to see that it becomes very blurry. You can, of course, see that also in the panel on the left. What you have here is the gate voltage as the y-axis, the tip sample bias is the x-axis, and the color scale represents the density of states. These two lines are the two sharp peaks of the two flat bands, and you can see all this blurriness that's happening in between when you have fully occupied these states, which are when they are below the chemical potential, or they're fully unoccupied over here when they're above the chemical potential. So this is actually the first surprising thing we observed, which is that why is it that these two sharp features, as you start to partially occupy them, they become extremely broad as you partially occupy the bands? Not only the state that you're filling just near the chemical potential, even the state that's very far away below the chemical potential also gets very broad. The basic message here is that this is caused by strong charge fluctuations due to the strong Coulomb interaction in the system. So it's a very hard problem to model theoretically, as I'll show you in a minute. But the first message that I want to show you just from the raw data, you can sort of see the energy scale of modification of the density of state is spanning basically 25 to 50 milli-electron volt, which is much larger than the bandwidth of the system. So now we look a little bit more carefully at these blurry region, and you can start to see that there are sharper features that are basically within this region of partial filling, and you can mark it by whether you have 4 electrons or 3 electrons per unit cell, Moiré unit cell, or 0, which is a charge neutrality, and whether you're basically putting holes there. Okay. I'm sorry, this is up to 8 electrons. This is 4 electrons, and this is no electrons, which is where you have -4. So you can see this succession of features that are happening every quarter filling in the system. To bring that out, we can take the di dv and divide it by I over v, which takes out the fact that your STM tip is actually moving up and down because of a set point when the tunneling current is changing dramatically. And what you can see here is this sharper feature comes out more clearly in the experimental results. So the system resets its property, and this relates to what Dimitri showed you, every quarter filling as you go through these integer filling of the system. So this is again related to the strong correlation in this system. But now you have to take into account that we have 4 degrees we have the flavors of the electrons, the spin and valley degrees of freedom. So you can kind of think about this in real space as the Moiré sites as a bunch of quantum dots. And these quantum dots have hopping between them. That's the width of the flat band. The energy of the flat bands, you can think of them as E naught and minus E naught. And then you have on-site and nearest neighbor Coulomb repulsion in the system. This is a very, very difficult problem to solve. The full many-body problem here is even more harder than the cuprates. So what you want to do in order to make progress trying to understand our results is to make some simple assumptions, like let's take the infinite U limit of this system where you have almost 0 hopping. And if you ignore the hopping term, you can begin to understand what the spectroscopic measurements are by basically simulating the electron addition and removal spectra of that infinite U Hubbard model. So what I have here is on the left is the calculations that come out of such a simple model. And on the right, I have the experimental results. And what you see, these 2 lines just represents to the 2 levels of the flat band. And then you see a successive number of features in between. This is just a quantum dot type of model. But what it does is it shows you schematically that the features that you see in the data, excitations that start basically near the chemical potential, go out to some energy and reset every time you go through these quarter filling, corresponding to the degeneracy of the system, the spin and the valley, is basically reflecting the Coulomb repulsion between the electrons, which determines the addition and removal spectral density in the system. So the features that are in this data, of course, require a more sophisticated model, which of course needs to have hopping terms. This model doesn't have hopping. And we have done some exact diagonalization with Andre Bernovic in order to understand these better. But I don't want to go into those detailed calculations, just to show you that this simple quantum dot model allows you to say that the energy to which this feature goes up to, basically even, for example, near charge neutrality, allows you to extract the strength of U, which is about 23 milli-electron volt in these samples. Now, I should add that the samples that we make, the gate actually is quite far compared to the samples you just heard about from Dimitri, where he tunes the distance between them. So that's actually kind of an interesting experiment to do. He also told you about changing the twist angle. And if we change the twist angle from the magic angle, all these correlated features that I told you about basically disappear. And if you have a question about that, I can show you those results at the end. So the relationship between these cascade of features in the spectroscopy and what you heard in terms of the cascades of correlated insulating phases is very clear. These large U features signal that the system has a sort of a Hubbard band-like model, where these Hubbard bands develop a sort of spin or valley polarization. Even at very high temperatures, they would like to perhaps the system knows about the fact that they want to go into some sort of a correlated state where the Hubbard subbands are separated, and you likely are making spin or valley polarized state, some of which I'll show you as we go along here. So these signatures of correlations are now becoming very quantitative with these experiments. Because now we can measure the additional and removable spectra and really establish that U is indeed larger than the bandwidth and is of the order of 25 millivolts. So incidentally, these experiments I showed you just now were done at 6 Kelvin. And this is sort of like the normal state property of the system before we get into the correlated insulating phases or the superconducting phases. Now, let me just say that when you take the samples to like 10 millikelvin with electron temperatures of like 200 millikelvin, you begin to see gaps develop, which are associated with the correlated insulating and superconducting phases. I'm not going to say a whole lot about them, but let me flash a few results. So for example, this is the point, this is the charge neutrality point. This is nu -2. This is when you have 2 electrons filling the lower flat band, or you have hole doping, depending on how you look at it. And what we do see is an insulating phase at nu equals -2, just like our transport colleagues see. And we see that nu equals 2 state, so which is where my arrow is. Let me show it. Is where you have a gap at the chemical potential, and this gap closes and reopens into a wider region, which is where very robust superconductivity has been seen in these samples, starting from the early work of Pablo. And you might ask, oh, what does a superconductivity look like? This is a work in progress, but I can flash a few results, which is that spectroscopically, it looks quite interesting. It doesn't look like your S-wave gap that you see in like an aluminum sample with a similar TC at the same temperature. Here you start to see some V-shaped gaps, and they have very unusual properties. So this is something we are working on. So let's see, I have another 5 or so minutes or 10 minutes. So let me switch topics and connect with Dimitri's discussion about topological phases and magnetism in this system. So as he pointed out, some beautiful work by David Hubbard-Gordon and Andrea Young showed us that when we have this magic angle twisted bilayer graphene samples aligned with the boron nitride sample underneath, the system begins to show magnetism, and it shows signatures of intrinsic quantum anomalous Hall effect, which is basically the system is showing you a quantized Hall conductance at 0 magnetic field. And it turns out, as Dimitri explained, this is related to the Dirac physics of the band structure of this system. You can think about the alignment with the boron nitride breaking the sublattice symmetry of the graphene lattice and opening up a gap at the Dirac point. And opening up this gap basically exposes the fact that what you started with, because it's graphene, has this Barry curvature, and from basically occupying this subband structure of these flat bands, you can create churn insulating phases. So this looked very exciting to us, but and we were trying to make devices that were actually aligned to search for these effects. But we found that actually we didn't even need to do that. Correlations allowed us to see in signature of the churn insulating phases. Now, there are a lot of STM experts in the audience, and they might say, well, how do you measure quantized Hall conductance with an STM? So, I'll tell you how. You get some smart people in your lab. So I didn't realize this, but some of my students did, which is that if you think about your system is a churn insulator, the chemical potential sits in an energy gap, and it gives you the Hall conductance, which is, of course, we all know to be quantized. But this is well known that if you combine this relationship with Maxwell's equation and Ohm's law, you realize that in a system where you can change the density and the magnetic field, by charge continuity, the charge density at which a churn insulating phase is observed changes with the magnetic field, because you're changing the degeneracy of the system with the magnetic field. So if you do an STM experiment and you have an insulating phase, even it's a churn insulating phase, you will see a gap. And if you follow that gap as a function of magnetic field and density, the way it moves, it follows this formula called the strata formula, the slope of which gives you the churn basically number of associated with that energy gap. So this is a extremely simple experiment. So I go back to what I showed you before. This was at the very low temperatures. These are the spectra. You see some gaps at low fields. Then you turn up the field. And this is a very rich system. It has a Dirac point, so you could have a zero lambda level. But what you can see from your eye is there are lots of gaps that are opening up in the system as you apply a magnetic field. And you notice that these gaps appear at some gate voltages. And these gate voltages corresponding to some density move as you change the value of the magnetic field. I know this is a busy slide, but what you can do is you can just take the center of those gaps and plot them as a function of magnetic field and as a function of gate voltage. And if you do that, you basically find that it does indeed follow the strata formula. You resolve the features associated with the zeroth lambda level, which is what's in the middle here of the plot near the charge neutrality point. But very similar to the experiments that you just saw from Dimitri, we were able to resolve that application of a weak field. It introduces these different churn insulating state, the churn number of which can be determined through this experiment. So you might say, well, why bother to do this STM experiment? It's so cumbersome, and you can just do a transport experiment. The reason this is important is that STM actually allows you to distinguish whether these churn insulating phases are caused by single particle physics or they're caused by many body interaction. Well, how does it do that? Well, the way it would do that is that if you observe a gap that is due to a single particle effect, it would not care whether your system is occupied or not. Here, the gap that is associated with these churn insulating phases of 1, 2, 3, corresponding to nu equals 1, 2, 3, the details of which doesn't matter to the non-expert, they only occur at the chemical potential. So what this tells us is that what's giving rise to these topological phases is interaction between electrons, not some single particle physics like alignment with the BN, or even the Hofstadter physics, which would also give you other gaps in this material. So we are beginning to understand how these many body states are formed together with Andre and other colleagues. And let me just say, I showed you the example where from David Gorhaber-Gordon and Andrea Young, how you get churn insulating states by breaking the AB sublattice symmetry. This is in real space. You can think about what we are observing as in momentum space. You have the K prime basically symmetry in the system. And if you introduce time reversal symmetry breaking, just like Haldane did in his famous model, you basically form these churn insulating phases that we are observing. That's the way it comes about in our experiments, is you have to break the time reversal symmetry. So the system has some magnetism in it, which is developing, and it's basically being aligned when you apply a little bit of magnetic field. All right, so as it was pointed out, there is exact calculations. Dimitri and I are dragged onto this paper with our theory collaborators, and the upshot is that there are many competing ground states. This is a very rich system near these integer fillings of 1, 2, 3, 4, and basically, as we apply a field, the understanding is that the high Chern numbers become favored. It just kind of makes sense. There is these high Chern numbers correspond to some orbital magnetism, which was just spoken about. So the magnetic field favors those states, and that seems to be what's happening, for example, near nu equals 3, 2, and 3. And what's interesting and is the next question is, how do these phases interact with superconductivity, which is what we're going to be aiming to try to understand next. So let me wrap up. I need to do two things here. One is to just tell you the big message here is that U is the largest energy scale in this problem, larger than the bandwidth, which is giving us this Hubbard physics, which we've seen in electron addition and removal spectra. And that's the beauty of interactions. It can do unexpected things. And it gave us these Chern insulating phases where we didn't expect them. And as is being asked in the questions, how is this superconductivity coming about is the next question. And I want to just, on a broader perspective, let me just say that this is a very rich field. There is just Moiré systems are coming out of the woodwork with a lot of different materials. And I think that the STM community can contribute quite a bit, as we heard through some of the talks in this conference, to what we see here in the understanding this system. So you will now get a glimpse of the fact that I have to wake up very early to make this talk. So the most important slide of this talk is missing, and which is what you realize when you give a talk, which is this one. Who's done all the work? The work has been done by Dylan, Kevin, and Mangshul. These are the people leading what I showed you mostly, and we have a broader Moiré team: Gelara, Cheng-Li, and Zhao Ming. And the theory is Biao and Andre, and some earlier work that I showed you got pioneered by Berthold and Young Long, who were in my lab before. So I want to thank you for your attention